If you're a first year engineering student or just want a basic introduction as to how electrochemistry works, you're in the right place, because this is essentially the place you want to start. So this isn't really a video made to watch at leisure. I recommend you take notes and research any terms you don't understand, because we want people out there who are educated when they're building batteries. So I'm just going to introduce the topic, and then we're going to talk about redox reactions and then common reduction reactions in aqueous solutions. So you must know that due to the atomic configuration of metals, their delocalized electrons make them the most giving out of all the three primary materials. An engineer can exploit the ability of metals to easily give up their electrons through electrochemistry, where the flow of electrons is controlled and harnessed to create power and make cars go fast. Before we understand which metals will spew the most electrons in which environments, we must understand all of the environments which metals will give up their electrons in. And so you understand why we don't make batteries out of marshmallows. And thus don't waste time experimenting where experimenters have already gone. So I'm going to tell you where everybody's gone, and these are the best environments. And this is, we'll see it at the end what I mean. So redox reactions. Don't be afraid. I feel like redox reactions scare a lot of people because they hear from other people that they're scary. They're not. It's just a transfer of electrons. That's all it is. It's just electrons moving from one atom to another on a mass scale. So usually when you hear transferring of electrons, you think about like atomic bonding. So redox reactions are slightly different in that the electron transfer doesn't result in these particular atoms sticking together. They just go in their separate directions. So redox has some meaning and care to it, which is why it seems a little alien at first. It's just redox. It doesn't have the most obvious name. You can't really tell what it means, but I promise it'll make sense in a minute. So when we investigate the exchange of electrons between chemical species, we use a specific chem language. So when we're building stuff, we can tell other engineers what's happening, and we condense all of these concepts into one word or two words. So when a metal gives up its electrons, it oxidizes. Yes, the oxidation of a metal is the act of it giving up its electrons. It's weird, but get used to it. Now, reduction is when a metal gains electrons. I know, we've had some scientists in the past, they name these things, we can't change it because it's so widespread. Just like conventional current and actual current, this is another situation of that. So I like to think of it as a reduction in charge rather than a gain in electrons, and that sort of helps it stick better. So let's say you got a free floating electron from an oxidation reaction right here. That electron is going to join into a reduction reaction and reduce the charge of the other element. So where does the oxidation of a metal and the reduction of another metal occur? Now, oxidation occurs at the anode and reduction occurs at the anode. Bit of a typo there. Reduction doesn't always necessarily happen at a metal, but for practical purposes, usually we involve two metals because their electronegativities are much better to work with than, say, something stiff like a noble gas. It's not a metal, and we don't really want to use that reduction because it doesn't want to give up any electrons. It's okay. So metals are the most reductive and the most oxidative generally. We'll see why that is later on. So yes, oxidation occurs at the anode, reduction occurs at the cathode, and this is how I remember which electron transfer occurs at which node. So there's a guy, he's actually Italian, and he's made a pizza, and he notices that his secret ingredient, the electrons, are gone. So he goes, "Oh no! His electrons have been lost." That's what his special spice. That was his special spice. So oxidation occurs at the anode, and that's how I find oil rig a bit boring. Like, this is much more entertaining. Then if you remember this one, then you can just remember the reduction happens at the cathode. So, use it. You feel free to use it. So then you can pretty much remember that just repeating myself. Some common oxidation reactions are iron, releasing 2 electrons, and aluminium, releasing 3 electrons. And reduction reactions, say hydrogen, gaining a couple electrons and will turn into gas, which I think is pretty cool. But we'll look at this in more detail in a moment. I'll finish explaining redox reactions. So as you probably figured out, the electrons lost in oxidation reactions facilitate the possibility of a reduction reaction, especially if engineers manipulate the environment to make this the only possible outcome. So why do we call these chemical reactions redox reactions? Well, I'll ease you into it. A half reaction describes the action of either an oxidation or a reduction reaction occurring. The electrons lost from oxidation are collected by the reduction reaction. Since this is a very common process in nature, we just refer to redox reactions when we want to start talking about electron transfer. And redox is just a portmanteau of reduction and oxidation. So as engineers, we're going to be interested in which environments are going to extract more electrons out of our metals. So let's have a look at some common reduction reactions in aqueous solutions. So what do you think is going to happen if you put a metal in acid, namely just an aqueous solution full of protons, namely just something full of hydrogen ions? Oh yeah, a reminder, an aqueous solution just means dissolved in water, for those who haven't brushed up on their chemistry in a while. You actually get hydrogen gas, and hydrogen gas is very, very, very flammable, so don't fill a Zeppelin with it. What happens if you put a metal in an aerated acidic solution? You get water. Can't really, because water's not that dangerous, so we're fine. What about putting metal in an aerated neutral or alkaline solution? You'll just get hydroxide ions. This thing. So what if a metal is dropped into an aqueous solution of other metals? What do we get? Well, it would depend on something called a reduction potential, but we'll cover that in another video. Essentially, either one of the metals will gain electrons, so as you can see here, and it will turn to neutral, or not become charged neutral and simply decrease by one charge instead of all the way. And those have specific names. I'll include a table at the end of the video. So to summarize, in order to harness the energy caused from the flow of electrons between metals and other elements, we need to understand if this is possible, and guess what? It is. It happens in two distinct steps, oxidation and reduction. Redox reactions for short. And yes, oxidation is the losing of electrons, and reduction is a reaction where electrons are accepted and the final product does not release any electrons. And I explain it there. We focused on which reductive environments metals will likely be exposed to and what products they will form. And that's pretty much what we had a look in this video, and it would be useful if you wrote down the following tables somewhere in your notes. So here's everything I just discussed, just properly and a lot less colloquially. So yeah, I hope you guys have a better understanding of what happens if you're not careful about where you put metals and why you should probably protect it against certain environments.